Hello friends, I welcome you to the lecture on variational problems of general type. So far we considered the variational problems which involved equations which were formed by integrating a certain differential expression. If you recall, we had considered such type of functionals. Now in practice we often come across more general cases classes of functionals. For example, let us consider the functional I phi equal to integral a to b kst into phi s phi t ds dt plus integral over a to b phi s whole square into ds minus 2 times integral a to b phi s into fs ds, which we wish to extremize. It is given to us that the function kst is a continuous function with the property of symmetry, that is kst is equal to kts, and fs is a given continuous function of s. Phi s is the unknown continuous function of s. Now in order to find the variation of this functional, we replace phi y phi plus epsilon zeta, and let us consider I we replace by I phi, we replace by I phi plus epsilon zeta, and let us assume that I phi plus epsilon zeta is equal to psi epsilon. Psi is the function of epsilon. Then we know that delta I is nothing but d psi over d epsilon at epsilon is equal to 0. So let us apply this formula. Let us see how we get the value of delta I. We have I phi equal to integral over a to b integral over a to b kst phi s phi t ds dt plus integral over a to b phi s whole square ds and then we have minus 2 times integral over a to b So in this functional, let us replace phi y phi plus epsilon times zeta. Okay, so replacing we have psi epsilon is equal to integral a to b kst phi s means phi we are replacing by phi plus epsilon zeta, so phi s will become phi s plus epsilon zeta s, phi t will be phi t plus epsilon zeta t into ds dt, and here we shall have phi s will become phi s plus epsilon zeta s minus 2 times integral a to b phi s will become into fs ds. Now in order to determine delta I, let us differentiate psi with respect to epsilon. So then d psi over d epsilon will be kst. When we differentiate this with respect to epsilon, we have here product of two functions which depend on epsilon. So we apply the formula of derivative of a product of two functions. So first we differentiate this, and when we differentiate this with respect to epsilon, we get zeta s into phi t plus epsilon zeta t plus. Now we differentiate okay, second function with respect to epsilon. So zeta t into phi s plus epsilon zeta s. ds dt, and then we come to this one second. So plus integral over a to b 2 times phi s plus epsilon zeta s, and then here when we differentiate with respect to epsilon we get zeta s. Now when we differentiate here we get minus 2 times integral a to b. This will be, when we differentiated this with respect to epsilon we get zeta s into fs ds. Now delta I is equal to d psi over d epsilon when epsilon is 0. So delta I is equal to, let us put epsilon equal to 0. So what we get, integral over a to b, then we get kst zeta s into epsilon is 0, so phi t plus in the second term zeta t into phi s. ds dt. And then we get 2 times integral a to b, when we put epsilon 0, phi s into zeta s ds minus 2 times integral a to b zeta s into fs ds. So this is delta I. When we put d psi over d epsilon, when we find d psi over d epsilon at the epsilon equal to 0, we get delta I, and now this can be put further in this form. This can be written as, now we can see here that this is kst zeta s phi t. Here we have kst zeta t into phi s. In the first integral, if you interchange s and t, the limits will remain the same. We will have integral a to b, here we shall get kts, and then here we will get zeta t into phi s, and we will get dt ds when we interchange t and s. Now we are assuming that kst and kts are same. This is first integral, first term in the above expression. So this is nothing but integral a to b, kst is equal to kts. So we can write kst into zeta t into phi s. Also we can write ds dt. Now we can write it, so thus we can write delta I as So the first term in the above expression can be written like this, and hence delta I is equal to integral over a to b zeta t times integral over a to b kst into phi s minus phi t into minus ft dt, and for the extremum delta I is equal to 0. So, hence so for an extremum so what we get, integral a to b zeta t times integral a to b kst into minus phi s, here it will be ds also. Now this I am able to write because this is the definite integral. Here when we change the interval, the variables s and t, what do we find? kst as kst becomes kts, but kst and kts are same. So we get kst and then zeta t phi s into ds dt. Here also we get zeta t into phi s ds dt. So this becomes double. Okay, so we get when we combine first term with the second term, we get twice integral a to b kst zeta t into phi s ds dt, and here these are definite integrals. We can change the variable of integration from s to t. So this will become 2 times a to b phi t zeta t dt, and this is minus 2 times integral a to b zeta t fs. This was ds. So zeta t ft dt. So that quantity we have written in this form. Now for an extremum delta is equal to 0, so we get this. Since delta zeta t is arbitrary, we have the condition that integral a to b kst into phi s ds minus phi t minus ft equal to 0, or integral a to b kst into phi s ds minus ft is equal to phi t, which is a Fredholm integral equation of the second kind. Now, so we notice that we get this Fredholm integral equation, which is the Euler equation, for the given variational problem, because this equation we are getting by putting delta equal to 0. So this is Fredholm integral equation. So what we want to emphasize is that the Euler equation for the given variational problem is nothing but the Fredholm integral equation, where phi is the unknown function. Let us now go to the second example. Let us consider this functional I phi equal to integral over minus infinity to infinity px into phi dash x whole square plus 2 phi x plus 1 into phi x minus 1 minus phi square x minus 2 phi x into fx dx, which we wish to extremize. Let us assume that the argument function is continuous and has a piecewise continuous derivative in the interval minus infinity to infinity. So let us see how we get the Euler's equation for this variation problem. So again what we will do is we will replace phi by phi plus epsilon zeta, and then we shall call I phi plus epsilon zeta as psi epsilon. We will differentiate psi epsilon with respect to epsilon and then put epsilon equal to 0 to get the delta I, and then for an extremum we know delta I is equal to 0. So when we put delta I equal to 0 and use the fact that zeta t is an arbitrary function, we shall get the Euler's equation for this variational problem. So let us see, we are given that I phi equal to integral over minus infinity to infinity px into phi dash x whole square plus 2 times pi x plus 1 phi x minus 1, and then we have minus phi square x minus 2 times phi x into fx dx. So let us put phi plus epsilon zeta in place of phi and call it as psi epsilon. Psi epsilon equal to I phi plus phi dash x will be phi dash x plus epsilon zeta dash x whole square plus 2 times phi x plus 1 will be phi x plus 1 plus epsilon zeta x plus 1, then phi x minus 1 will be phi x minus 1 plus epsilon zeta x minus 1, minus phi square x will be phi x plus epsilon zeta x whole square, and then minus 2 times phi x plus epsilon zeta x into fx dx. So let us differentiate psi with respect to epsilon. So d psi over d epsilon will be equal to minus infinity to infinity px, derivative here will be 2 times phi dash x plus epsilon zeta dash x into zeta dash x, plus here what we will get, the product of two functions of epsilon we have. So 2 times phi, when we differentiate this with respect to epsilon we get zeta x plus 1 into phi x minus 1 plus epsilon zeta x minus 1, and then we differentiate the second one. So phi x plus 1 plus epsilon zeta x plus 1 into zeta x minus 1, and then we come here. So minus 2 times phi x plus epsilon zeta x into zeta x, and then we come here. So we get what derivative with respect to epsilon will give you zeta x here. So to minus 2 zeta x fx into dx. Now let us put epsilon equal to 0 here in order to get delta I. So then delta I equal to is equal to what we will put epsilon equal to 0 here. So we get minus infinity to infinity px, then here we get 2 phi dash x zeta dash x here we will get 2 times zeta x plus 1 into phi x minus 1, and here we shall have phi x plus 1 zeta x minus 1. Then we have minus 2 times epsilon equal to 0, so phi x zeta x, and here we get minus 2 zeta x fx dx. As we know, for an extremum delta I equal to 0, so what we will get, minus infinity to infinity, we can write it as px, we can divide the whole equation, this is equal to 0, and after that we can divide the whole equation by 2, so px phi dash x into zeta dash x dx plus now integral over minus infinity to infinity zeta x plus 1 phi x minus 1 we can put as replacing x plus 1 by x. What we will get, the limits will remain minus infinity to infinity, so we will get zeta x phi, in place of x we are putting x minus 1, so x minus 2 plus, in the second one we are putting x minus 1 in place of x, so phi, no, in place of x minus 1 we are putting x, so x is replaced by x minus x plus 1, so phi x plus 2 zeta x, and then here we get minus 2 phi x zeta x, sorry, not 2 is divided, phi x zeta x, and then we get minus zeta x fx dx equal to 0. Now we do the following. Let us look at the first integral here, integrating by parts, px into phi dash x into zeta dash x. We may write this is equal to integration by parts. So this I call as one function, this is second function. So minus, sorry, so we have integration, first function into integral of zeta dash x, which is zeta x, derivative of first function, so p phi dash x, px into phi dash x dash derivative of the first function into zeta x dx. Which is equal to minus integral minus infinity to infinity p phi dash into zeta x dx, where we assume that px tends to 0 as x tends to plus minus infinity. So this quantity goes to 0 as x goes to plus minus infinity. Now putting this value here, okay, so then delta I equal to 0 will imply that first term will be replaced by this, okay. So what we will have, minus infinity to infinity p phi dash okay, we will take zeta x common from all the terms, so minus phi x minus 2 minus phi x plus 2, okay, plus phi x plus fx into zeta x. We get this. When we substitute this value here, okay, multiply the whole equation by minus 1, we get this. Now since zeta x is arbitrary, we get p phi dash dash minus phi x minus 2 this equation, which is the Euler equation for this problem, and we notice that this equation is nothing but the difference equation for the argument function phi x. So such variational problems are often encountered in practice, where we, in the first case we have seen that we get the Euler equation as the Fredholm integral equation of the second kind, and in the second case we get a differential difference equation for the unknown function phi x. Now let us also consider, next we consider variational principle for the equation y double dash x equal to fx by y dash. Okay, so let us consider the variational principle for the equation y double dash equal to fx by y dash. What we notice here is that any equation of this type is a Euler equation for some functional I by x equal to integral x1 to x2 fx by y dash dx. How we will show this? Let us remember that the necessary condition for an extremum of the equation I by x equal to integral x1 to x2 fx by y dash dx is delta f over delta y minus d over dx of this. We know already that if we have a functional like this, then the necessary condition for an extremum of this equation is this. Now this Euler equation can be put in an alternative form as delta f over delta y minus delta square f over delta x delta y dash minus y dash into delta square f by delta y dash minus y double dash into delta square f over delta y dash square equal to 0. So if the given second order differential equation is a Euler equation for the functional given by 3, then it must coincide with the second order differential equation, which is the equation number 4, which implies that there must be an identity with respect to x by n by dash. So what we will get, the equation 4 will then become fy minus fy dash x minus y dash times fy dash by minus fy dash by dash, and then this y double dash we shall replace by fx by y dash. This is given to us y double dash x equal to fx by y dash. So this will be replaced here, and then what we will do is let us differentiate this equation with respect to y dash. So we have fy minus fy dash x minus fy dash times fy dash by, and then we have fy y dash y dash into fx by y dash equal to 0. fy minus fy dash x minus y dash times fy dash by minus fy dash y dash fx by y dash equal to 0. Now this equation we differentiate with respect to y dash. So what we will get, we differentiate this with now differentiating with respect to y dash. What we get, fy y dash minus fy dash x y dash minus derivative with respect to y dash will give you, the derivative of y dash with respect to y dash is 1. So, f y dash y minus minus y dash times f y dash y dash, and then we get f y dash f x y dash minus f y dash into delta f over delta y dash equal to 0. Now, f y dash is same as f y dash by assuming the continuity of second order the partial derivatives here. So, this will cancel with this, and then what we get, we will get the equation as f y minus f y dash x minus y dash f y dash by minus f y dash into f x y dash with equal to 0 with respect to y dash. We arrive at the equation this which is nothing but f y dash x plus f y dash by into y dash plus f y dash into f plus f y dash into f y dash equal to 0. Now, let us set f y dash to be equal to u. Then this equation will give you partial derivative of u. First term will give partial derivative of u with respect to x plus y dash times partial derivative of u with respect to y plus f times partial derivative of u with respect to y dash plus f y dash into u equal to 0. So, thus in order to find the functional that is the function f x by y dash, we have to solve the above PD for the function u, and then we have to do the subsequent quadrature, because once u is known, the functional f can be found from the equation u equal to f by dash by dash. With that, I would like to conclude this lecture. Thank you very much for your attention.